record. Any questions regarding the okay, right. This computation? Okay, so we mentioned already that let me do we're recording, yeah, right? Yes, we are recording, and but then I didn't share yet. Okay, so I'm sharing now, and we mentioned already that the x axis and the u axis are coincident. That's why here you have 1, 0, 0, and v is that, and w is here. So we finished this one already, and we finished that, and then now we look at w. So w is again the unit vector. It doesn't have any component along the x because it's staying on this flat surface. So that's a 0. That's correct. And then now the w is it's a unit vector. So w times the negative of sine alpha. So where is alpha? So here is w from here. Okay, it moves to there. So that's alpha. Okay, so sine alpha is this. Okay, but because it is along the negative y already, this is negative y, so that's the negative. That's why it's negative of the sine alpha multiplied by the u. That's a unit vector, so that means that's a 1. Okay, and then here w again multiplied the cosine. So along the z-axis, that's alpha cosine. So this is the w cosine of that. This is that component, and that's positive because along the z-axis positive. So that's cosine alpha multiplied by the w unit vector. Again, that's a 1, and it's a 1, and so we are left with that. Okay. So now it is clear now that rotation of x about x by a value alpha is expressed using this vector. I mean this matrix. Okay. Now let's move on. Now we want to consider the rotation of the basic rotation around the y-axis. So the same principle. So if this is the y, so this is the y-axis, and we rotate about the y-axis by minus 90. Why is it minus 90? By the right hand rule, if this is positive and you rotate like that. But if you rotate this one, positive rotation is going in that direction, but because we are rotating in the other direction, like oh, you're bending my hand like this, so it's negative. So positive direction will be like this. It's easier. So now it's a minus 90 degrees. And so previously your u was here, and now your u is there, and previously your w was here, and your w moves there by minus 90 degrees. So this is what it looks like. So now if we consider facing from here, okay, and you rotate, in this case here, you rotate in the positive direction. This is your y-axis, and this is your v-axis. Okay, v and y are coincident. So because this is your u, v, and w, so your v has no component in the x and the y because it doesn't move. It's coincident there. So this is 0, and that's 0. And it's moved along, I mean, it's just lying along the y-axis. So the entire vector is along the y-axis. So that's 1. So 0, 1, 0. We are done with this one. Okay. Now, what is u with respect to x and z axis? Okay. So this is your u, and you take the component along the x. So this is your u cosine of phi. Okay, we rotate by phi. So this is u of x. So u cosine of phi, that's correct. And then what's the component along the y? It remains in this plane, no component along the y, that's 0. And then now, what is a component along the z-axis? it is a sine of phi. So that's sine of phi, but along the negative z-axis, so that's a minus sine of phi. Again, because your u is a unit vector, so there's nothing there. This is 1, is an identity. Okay. So next, where is your w? Your w now is this. So component along the x-axis, there's a sine of phi. So the sine of phi there. This is that component, the sine of phi. And then no component, this is correct. No component along the v, that's 0. And then component along the z-axis is cosine of phi. So cosine of phi, that's correct. So now if you rotate about y with respect to an angle of phi, then this is the standard equation. Cos sine minus sine cos, and 0, 1, 0, and then here is 0, 1, 0 as well. Okay. So next, clear all drawings. Go to the next slide. The last one is rotation about the z-axis. Again, you have, okay, just for the sake, just to finish off this discussion, although we are using the same principle, but I want to finish so that students will see the completeness. If you don't complete it, students won't understand correctly. So again, this is your W, which is coincident to the z-axis. So here, W and Z remains the same, and then you rotate by 90 degrees. Okay. From the top, you rotate 90 degrees. So here, your U was here, and then it moves there. Mr. Buaho, you're not looking. What are you looking? Oh, you're looking your screen. Okay. Okay. So there, that is your U. And then now your U moves from there to there, and then your V used to be here, your V, and then your V moves from here to there. Okay, so you will rotate by 90 degrees. The flat box that was here now rotated 90 degrees over there. Okay, so now what if we rotate by some arbitrary angle? So we say that your Z was here, axis, and your W is here. Okay, so W is coincident with the Z. So the whole W is in the Z axis. So here, that's Z, and this is Y, and that's X. Okay, so the entire W is along Z, no component of the X and the Y, so that's 0 and 0. Okay, so what's the component of the U with respect to X and Y? So U with respect to X, that's a cosine of phi. So here, cosine of phi, that's correct. And then Y is sine of phi, that's correct. No component along the z-axis, that's 0. Next, what's the component of V, which is along X? Along X is this one, sine of theta. But because this is along the negative X, so minus sine of theta. And then here is along Y, cosine of theta, that's correct. No component along the z-axis. Okay, so now we have completed the discussion of the basic rotation matrices. So in this case, you rotate about Z by an arbitrary angle theta. This is the rotation matrix. Okay, so now, so these are basic rotation matrices. What if we say we want to rotate into arbitrary, we want to rotate into some arbitrary axis, not just by X, by Z, and the Y, like that. We want to have like a combination of all of them. So how do we do that? So if you want a combination of all of them, well, that's easy. All you need to do is just take the combination as well in terms of the rotation. So, well, okay. Anyway, so before we arrive into that combination, we are going to see first how the vector P is being projected into the from UVW, okay, reference frame into the X, Y, and Z reference frame. Or in other words, the same thing as what we have discussed already is what this was frame 2. So from frame 2, P from frame 2, rotate, you rotate 2 with respect to 1 in order to get a vector P that is expressed in frame 1. Okay, this is just, these are identical. Okay, these and that are the same. Okay, so these are just mathematical expression that people use to write in order to fully express what's going on. So when you have P, U, and V, so the other way of writing this one is that you have your 2 of P, you have components in equal to P about U and P, okay, along U, along V, and P along W. Okay, that is in vector form, but because we want to express them, we want to express them in terms of in one equation, not in terms of components. So just one addition of components. So this is how we can express it mathematically, is that the P of U along the U axis multiplied by the I, which is a unit vector, okay, component along the P value, okay, the scalar value of PV, that is multiplied by the unit vector JV along JV, and then this is the X W value multiplied along the unit vector KW. Okay, so what is that? U, 1U, that is just 1, 0, 0. Please make note. What is JV? That is 1, 0, 1, 0. There's a vector 1 along X, 0, 0 in the Y. No component along the X and Y, or the along the X and Y component. Well, it's U, V, and W, but just to easy discussion, this is the X component, that's Y and Z, nothing. And then the J vector, there's only the component along the Y, no component in the X and the Z axis, while for the K, 0 component in the X and the Y, only component along the K. So if you write it down, it will come out with this one. You see it? PU times 1, so it becomes PU 0, 0. Okay. I'm just showing you how that mathematical expression is being used. So PU 0, 0. This is corresponding to this term. Plus 0 PV 0. Yeah, that corresponds to this term. Plus 0, 0 PW. Okay, that corresponds to the last term. Okay, you add them together, it will result in this. Okay, it's the same thing. Okay, well, the strength of this expression is that you just have to write the equation in equation form into symbolic form, not like this, not in the vector form. Okay, so anyway, so okay, let's clear out. Do you understand that? Any questions in that? It's just another way of expressing. So this is okay. So now we are going to get PX, PY, and PZ, okay, or PZ. Okay, that is, these are the components of your 1P. Yeah. Yeah. So now what we need to do is that your 2P, you take, this is your 2P. You're going to project. You project your P in terms of the X axis, project your P in terms of Y axis, and project your P in terms of the Z axis. Okay, you're just taking the components of the P that is along X, along Y, and along Z. So there, so that you can express this. So again, mathematically, this was this one, okay, and this was this, okay, and this was this, okay, and then all of them okay, along, this is the whole P. This is the whole P here. This is 2, okay? And then they take each component of along X, along component along X in the U, okay? Take the component along X in the okay, the components in the X in the frame 2, taking the component the X in frame 1, and Y component in frame 2, the X component in frame 1, the Z component in frame 2 times I'm taking the X component in frame 1. Okay, so what is similar to what we did in the previous slides, where we are taking each of these axis components into the stationary axis X, Y, and Z. Okay, so what it's trying to do is that from the 2, you take the projection of this P of 2, okay, expressed in the X, Y, and Z of frame 2, okay, and now know what is that component along the X in frame 1, this one along the X in frame 1, along the X in frame 1, and add them together to get the X component along the frame 1. Okay, so the same thing is being repeated here. You get again the same components of P expressed in frame 2, and now you get what are the components, the projections along the Y-axis of the frame 1. So along Y-axis, the same P2, 2P with respect to its own X-axis, 2P with respect to its own Y-axis, 2P with respect to its own Z-axis, and then projected into the Y component of the stationary axis. So Y component, Y component, Y component. We repeat the process. The Z component in the for each component of the 2P now taken or projected into the Z component of the stationary frame. Okay, so if you remember in your previous mathematics linear algebra, it's taking the components. If you take the projection, or you want to know the components of the vector, you project it with respect to a certain axis. In this case, project it with respect to the Z-axis, which is this. So the projection of P with respect to the Z-axis is this, PZ along the Z-axis. The projection of the P vector, okay, graphically, it will be just like what we mentioned before. Okay, like that. So this is P with respect to the Y, which is that. And this is P with respect to the Z. You're just taking the projection of those vectors. And this is the mathematical expression. And the along the X. Okay? Okay. What they're saying is that this rotation, what is that? What it does is that this rotation matrix, what it does is it takes the projection at every axis, okay, at every axis X, Y, and Z of the stationary axis 1 against the projection, knowing it takes the projection of that vector that was expressed in the rotated frame 2. Okay, in this case, this is the 2P, and then what is that expression in terms of rotated vector? I mean, rotated frame 2. You take each of those components projected into the stationary frame 1. Okay, that is what is being computed here. If you express this, it's just saying that these are the mathematical, this kind of matrix computation has this mathematical computation. Okay, that's all what it is saying. Okay, let's continue. So now it's just a simplification of what was here. Okay, you remove, because there's a common term here. Okay, if you make them into this is a vector, and then you can separate this maybe I should. This whole thing can be written as a vector. And then if you do that, you have a certain matrix like that and a vector PU, PV, and PW. Okay. Okay. And then, you know, the matrix computation, you remove this, you remove this, you remove this, because these are already here. And then there's no more addition. There's no more addition. Okay. So it will be this component, the first component of the matrix. I mean, the first column is the second column of the matrix, and the third column of the matrix. No more addition, and these values goes in here. Okay, it's just trying to make it into a matrix form. So here, so the same thing, this one goes here, and then this, there's no more addition, and this becomes a matrix. So this matrix form is actually the R. You understand? So they separate this, they simplify this into a matrix form to put P, PU, PV, and P here. So this is a matrix form, PU, PV, and PW here. So that is equal to PX, PY, and PZ. And so this is just the rotation matrix. That's all. So this is the rotation of 2R1 from P2, and this is P1. Any questions? Okay, let's continue. No questions. Those are just analytical computation of how the rotation matrix is, what the rotation matrix is doing with respect to two vectors expressing in two different frames. So now, if a vector can be expressed in terms of P1, again, we already have mentioned this before. If you can express it in terms of P1, so there is a rotation matrix 1 with respect to 2, such that you can express it in terms of P2 to P. Yeah. So that means that if we can do that, and we know that 2P is equal to, what is this? Okay, 1P, sorry, we just rewrite it. Okay, 2P is equal to 2R1, 1P1, and we know that 1P1, or 1P is equal to, what is that? 1R1, or 1R2, 2P. Okay, so if we do this, 2R1, okay, and if, for example, we assign this as a Q, okay, let's follow their convention here so that we don't create confusion. Let's follow the convention that this one is Q. So this is Q. Okay, we replace this as Q, 1P. Okay, so Q1, 1P is this one. So we can replace Q, 1P is this, 1R2, 2P2, 2P. Okay, so this one cancels. So that means that this one is 1. Q times 1R2 is equal to an identity matrix. Okay, so that means what? That means that 1R2 inverse you go on the other side, so 1R2 inverse is equal to Q. Okay, and what is peculiar about this is that the inverse for rotation matrix is equal to the transpose. You know why? That inverse is just the transpose. You know why? Anyone can answer me why, from our discussion, even from this one, why is the inverse equal to the transpose? Mr. Tomisang, you were late. Why? I mean, can you just roughly explain what could be the explanation why the transpose is equal to the inverse? We say, for example, here, Q is the inverse of R. So what we are saying here is that in our convention of 2R1, like that, where this R is 2R1, okay, the inverse of 2R1 is equal to our convention of 1R2, where your 1R2 is the Q, and then your 2R1 is the R. Why? And we're saying that that inverse, 1R2 inverse, no, sorry, this should be 2R1. Hold on. We're running out of time. Okay, let me write it here. 2R1 is equal to 1R2 inverse, and so also equal to 1R2 transpose. Why? From here, we just write our equations. Anyone? We say that to express your 2P into frame 1, you multiply it with 2R1, 1R2. And to express it in terms of frame 2, the frame 1, 1P, you multiply it with 2R1. Okay? So here we say that we can say that you take this inverse, okay? So you can take 2P2. So this one, 2R1 must be equal to 1R2 inverse, right? Mathematically. Okay? Yeah, that's correct. That's true. But now the question is why this inverse is equal to a transpose? Well, this one, first of all, is a property of orthogonal matrices, or unit orthogonal matrices. There are orthonormal. Yes, that's the term. Is a property of orthonormal matrices. Okay, unit vectors that are orthogonal to each other. Okay, if that is the property of the matrix, each column is a unit vector that's orthogonal to each other. The inverse of that matrix is the transpose. Okay, so that's a property of orthonormal matrices. But in this case, I want you to explain, based on our discussion, how come the inverse here is equal to the transpose? Okay, well, to answer that, maybe let me just answer it. Yeah. So remember, for example, in this case here, you say you have the component of Okay, let's just discuss based on UVW that we discussed. Okay, time is running, so whatever is remaining, we can U, V, and W. Yeah, and here is the X, Y, and Z. Okay, to get those components. Okay, and to take U, V, and W. Okay, remember, that's how we take the components. You multiply with, okay, so here, that means that here you can express PU, PV, and PW to get your PX, PY, and PZ, right? Right? Right. Yes. And then now, when you want to get your PU, PV, and PW, well, your matrix has to be, here is the X, Y component and the Z component, okay, where you have PX, PY, and PZ. Okay. Well, what is this? You have your X component, the Y component, and the Z component. Here you have the U component, V component, and W. Well, if this matrix is the inverse of that matrix, okay, because here, this is what we define. That is the inverse. One matrix to show the 2P expressed in P1. That's one matrix. Another matrix to express 1P. This is the 1P to express in terms of P2. So that means this matrix is the inverse of that matrix. But what is this? Well, it's just a transpose, because you see, used to be the X, Y, and Z is here. You transpose that, you take the other component, U, V, and W on that side. Okay. You understand? These are identical. This is the same as that one. This is the same as that one. Okay. And these are two different matrices, but we are saying that once you transpose this matrix, you can get exactly this value. So because this is the transpose of that, and also this is the inverse of that, so that means that the inverse is equal to the transpose. Okay. You understand? Okay. Okay, just think about it, and hopefully next meeting it will be clear to you. If you have more questions, you ask me. Okay, so next meeting we will discuss about, it's going to be 1 o'clock now. We're going to discuss about some examples here, but you can work on your own. I think these are self-explanatory, just the rotation matrices. And now when we have composite rotations, that means that multiplication of several basic rotation matrices in order to come out with the final rotation matrix. Okay, so here we'll just discuss some examples, and then now we want to know several basic rotations to come out with the final rotation. Okay, and then we'll also do this one is just maybe we won't have we won't go into much details on this one, but I want you to understand that you can also rotate, you can perform those basic rotations to come out with an arbitrary rotation about an arbitrary axis, okay, based on the basic rotations. You combine basic rotations, you can come out with rotation about an arbitrary axis, okay, and then we can compute arbitrary axis rotation and some Euler representation, okay. I want you to understand this roll, pitch, and yaw that is being used by many. And I don't want you to be confused about that convention. Roll, pitch, and yaw can be quite confusing if you don't understand exactly what's going on. Okay, we'll discuss about that roll, pitch, and yaw, and then we will show some examples of computation. Okay, And then after that, okay, we combine the rotation matrix and the position matrix into a transformation matrix. Okay. Once you have that transformation matrix, now it's easy to transfer from many different frames. This is what I'm leading to in this all this discussion. I'm leading towards this transformation matrix that will make things easy, so that now we only compute based on matrices. This is the matrix that we are going to transfer to many different frames accordingly by just pre-multiplying or post-multiplying this matrix, okay, which is composed of a rotation matrix and a position vector. Okay, so in this case here, you're considering both position change in position as well as change in orientation at the same time in one matrix. Okay. Okay. Any other questions? Okay. I just gave you a heads up so that next meeting you can think about it, and you can have an initial understanding of what to expect next meeting. Okay. So the next lab, of course, our lab will be mostly exercises, computational exercises. The next lab will be about these rotation matrices and